Okay, we're back, and I'm going to show you a few kind of interesting examples of things you can simulate here with this wave simulator that we have written. At the end of the last video, I showed you how to make this standing wave by making two identical waves traveling in opposite directions. Usually this manifests itself from a wave reflecting off of a surface and coming back. So waves that are confined between reflective surfaces will have some pattern of standing waves like this. But every type of homogeneous wave, which is a wave that is traveling at the same speed over all locations, so like a sound wave traveling through air, uniform air, always is made up of some superposition of pure sine waves like this, even if it's a weird shape like a square wave. And we can demonstrate that. The sort of formula for making a square wave, I'm going to actually make the frequency 0. We're just going to make a stationary wave, so it's a little bit easier to see. But if you just use odd values for the wave number, and you use 1 over the wave number for the amplitude, so that would be 1, 3, 5, 1 over 5 is 0.2, and so on. You can see the individual components back there, and the superposition is, not really a square wave yet. You need to use quite a few component waves in order to converge to a square wave, but it's very easy to, in a computer program, fill in as many of these waves as you want. We could make a series of 100 of them if we wanted. It would be annoying to type all of those in, so I'm going to show you how to make a button that when you push the button, it will populate all of the wave parameters with the right parameters required to make a good square wave. Just one thing first here. I don't like using this index. I forget what these are called. What are they called here? I guess it's just called an index display. I thought there's another name for it. But I think it'd be more natural to use like a scroll bar. So you can edit that easily. Visible items, turn on a horizontal scroll bar there. Turn off the index display. And now if you have too many waves here, if I make this smaller, you can scroll between all of the different wave parameters without having to use the little number deal. But okay, how are we going to make a button to populate all of these, like 100 waves, to make a really good square wave, for instance? Well, first thing we need to make is a button, which on the front panel you can find in the Boolean palette there. An OK button is fine. We're going to just replace the text there with, make square wave, something like that. And we'll name it that too. But we don't really need to display that label on the front panel, so we'll just uncheck that. And you'll see we get this little Boolean icon there in our block diagram. And these buttons are they're Booleans, which means there's only two possible values for them, true or false. They're either on or off, which makes sense because a button is either depressed or it's not. And we want this to, whenever the button is pressed, to do something here. So what I'm going to do is add inside of this main loop a case structure, another type of structure here. I'm going to wire the make square wave button up to it, and you can see now there's two windows here of this case structure, true and false. And you might have already guessed how this works, but if the button is depressed, meaning it's true, it will execute, the program will execute whatever code is here. And if it's not depressed, it will execute whatever code is here in this window. If the button's not depressed, we don't want it to do anything. So we're going to leave this false case blank. But in the true case, we want to change the values of this all waves cluster here. And let's make a for loop. And let's make, let's say, a superposition of 100 different waves for this. We could make this a control if we wanted, but I don't know how often we're going to use this, so I'm just going to make it a constant. And we're going to generate all of the amplitudes and k values, wave numbers for, you know, the first 100 in this series that makes up a square wave. So that's going to be the odd values of I for k, because 1, 3, 5, 7, and so forth. So how do we only get odd values here? Well, we're counting up by 2 every time, right? So we want to multiply I by 2. Just a constant 2. And then we want to add 1, because if we don't, it'll be even numbers. It'll be 0, 2, 4, whatever. But if we add 1 to it, which you can do with this increment function, now it'll be 1, 3, 5, and so on. That's our k's. And then we also want to calculate a, which is going to be 1 over this number, which is easy and numeric. There's a reciprocal function. So we'll do that. We can just keep the phase shift 0, because this is a superposition of sine waves to make a square wave. And we can make f 0. And so we need to make a cluster like this. It's important that you bundle A, F, K, and phi in the right order. Otherwise, you know, you're gonna be assigning the wrong number to the wrong variable there. Let's see, what's the easiest way to do that? Let's just try. I think it should be in the order I put them in the cluster here. So I'm going to, I guess the easiest way is to do a bundle by name. Let's just do a bundle. And so A on the top, then F, which is just going to be a constant 0, then K, which is this 2x plus 1, then phi, which is also a constant 0. I'll just use this same wire. And now we've created a one of the parameter sets here, but since it's in a loop, this is going to go 100 times, and we're going to end up with a whole array, which we can just write to this all waves control here. So how do we make this control be this value? And we've already used it up here. The best way to do that is to right-click on the control, go to Create Property Node, and this is where you can edit all of the different properties of the control, like its color or its size or whatever, but also just its value. So I'm going to go to Create Property Node, All Waves, Value. By default, you're reading its value. We actually want to write to its value. We want to make its value be what we say it is. So if I wire up this array of clusters here to value, and then we press this button, it should do that for us. So just to check, I'm going to delete A couple of those, just so you can see it populating. And then I'm going to click Make Square Wave, and you can see now this is following the right pattern. 1, 3, 5, 7, so forth. And over here on the superposition, you can see, you know, a lot more easily a square wave. There's a couple little deviations there, but if I make this even more square waves, like 1,000 square waves, which the program shouldn't have any trouble handling, then you get basically perfect, a perfect square wave shape. Okay, so you know, a lot of times you see these infinite series when you're doing math by hand, and it seems impractical because you would never be able to calculate that in real life. But this, you can do it really easily with a computer. And in real life, the thing is, you don't have to make this square wave through a superposition of sine waves. In fact, it's usually more natural to make this square wave pattern. For instance, say you wanted to make a square wave with a speaker. It's really easy. It doesn't even take very much data to play that sort of sound. It's just a matter of turning the of moving your speaker membrane back and forth very suddenly. Okay, so you just move your membrane back and forward and back and forward. But the sound waves that you make by doing that, if you were to do a look at the frequency spectrum of it, it would have all of these sine wave components. Okay, so whenever you see these kind of waves in nature, it's always made up of this superposition of pure sine waves, even if that's not how it was physically generated. So it's a little bit weird, but it's pretty cool. Gives you some insight into the way the world kind of works. So that's how you make a square wave. But there's some other things you can do here that are a little bit more relevant to quantum mechanics, because actually the uncertainty principle is not a uniquely quantum mechanical thing. There's a specific version of the uncertainty principle where you're just applying the general uncertainty principle to particles with mass, Heisenberg's uncertainty principle. But the general uncertainty principle we can demonstrate here pretty easily. First thing I want to do, I want to delete. I just made 1,000 of these clusters, so we would also like to make a button that just deletes them all, so we can put in a new set. So you should have an idea of how to do that now, but we can make a new button. And let's just type in clear array. And I'll just call it clear. Whatever I type up here is what it shows up as on the block diagram, by the way. That's why I'm bothering to do that, even though I am turning that off. Let's have another button down here. Let's make another case structure. In the false case, again, we don't want to do anything, but if you happen to press that button, you want to make this all waves parameter empty. And so one way to do that would be to you know, we could use this same cluster actually. We can just make a kind of dummy cluster here. It just needs to have 4 numbers in it. I'm just going to make them all equal to 0. Doesn't matter that one of them's an integer, or it shouldn't. We'll see if it gives me an error. And we're going to initialize a new array where all of the elements are equal to this, sort of everything is 0. But most importantly, the dimension size, which is how many elements are going to be in this array we're initializing, is going to be 0. And we're going to write that array to the all waves control there. I just copy and pasted this. You could also do the same thing we did before, where you right click on the control, go to create property node value. But let's see if this works. Clear array, there we go, and it's emptied out. Cool, so now you're kind of getting an idea of how to build interfaces. Let me show you an uncertainty principle. So the uncertainty principle has kind of, there's a couple different versions of it, I guess. There's the frequency time uncertainty principle. There's the position momentum uncertainty principle. And we'll do the position momentum one first. They're both conjugate variables. But momentum is directly related to the wave number, k. We learned about the de Broglie equation in class. And what it says is if you know if a wave is confined to a narrow region of space, if it has a more definite position, then it has to be made up of a broad range of wave number or momenta. So we can show that. I'm going to make a bunch of cosine functions because those are automatically in phase with each other. So we're going to phase shift all these by 0.25. That's how you turn sine functions into cosine functions. And we're going to keep the frequency 0 again, just so that it's stationary. Amplitude, we'll just make everything 1. But if we use some range of k here, and let's auto scale that, and let's zoom in here. Oops. You have to restart the program to update the x coordinates because we have that outside of our loop instead of inside of our loop. Then you see this weird superposition happening. Actually, I think I'm using numbers that are a little bit too far apart here. Oops. Let's keep going with this. Just need a lot of sine functions that are have different k numbers. And I don't know how many I'm going to need before it becomes obvious what's happening here. So instead of maybe doing this by hand, we should just put it into the code. But I'm going to keep going a little bit longer. But what you can see is here, as I'm adding all these component waves, since they're cosine functions, they all have their minimum or maximum value at 0. Since we shifted it by positive 0.25, it's actually the negative value. But if we made all of these negative 0.25s, it'll be a true cosine function. So there we go. You can see that all of these waves have a maximum value right at 0. So when you add them together, the middle of your function is getting really big. And but because these all have different k values and wavelengths, they're not in phase with each other as you get farther from the center here, and they start to cancel each other out. Although we haven't seen that quite yet for the number of waves that we're putting in there. So let's write another bit of our code that can generate again some large number of waves with some sort of pattern to them. So let's do, you know, kx uncertainty. And here we go. Oops. And we'll make a case structure. And let's do another for loop. And this time let's do 1,000 waves again. We want to make a cluster, same as before. The top value is going to be our amplitude, which we'll just set at a constant 1. The next number is our frequency, which we'll just set at a constant 0. The next number is k, which we want to actually vary. So let's do it similarly to how we did the making of the x points. In fact, we can just reuse that sub-vi, because what we want to do is we want to generate a list of numbers for k between some minimum value and some maximum value that are evenly spaced. So that is exactly what this make x sub-vi does. And even though we're not actually making x points, we're making k points, it doesn't matter. You know, and if we're doing that, we can actually do this outside of the loop. So there's 1,000 points, or 1,000 different k values that we need between some k max and, oops, get that wired into the wrong one. K max and k min. That's going to make a whole bunch of k values here, which we can auto index into our loop. And for phi, we want that to be a constant negative 0.25. Then we can write that to our all waves control. Oops. I'm copying these things, by the way, by just holding down the control button. You can copy anything if you hold down the control button and click on it and then drag. So let's see if this works. I'm going to run the program. For k max, let's do 5 and 1. Okay, there you go. You can see that with those 1,000 wave numbers, or 1,000 waves with wave numbers between 5 and 1, you get this pattern. So it's definitely more of the wave is seen in one position than the others. Let's try a larger range for this, though. And you can see if we have a broader range of k values, you get an even narrower kind of width to where in space your wave is. And, you know, you can keep going. And it'll get narrower and narrower. And you can actually show that this width is inversely related to the delta k there, which is in this case, you know, 29. That's how many, that's the width of our k values there. And so it actually demonstrates the uncertainty principle. You can also do it with the frequency and time. You'll see that the wave if you give it a range of frequency values instead of a range of k values, the wave will start off at some maximum amplitude and it will gradually shrink to 0 after some inversely proportional amount of time to your delta f. Yeah, if you're in my class, you're going to get a set of practice problems that involves doing this a little bit more quantitatively, but that is the main idea.